Assalamualaikum and hi everyone. The topic for today's lecture is on bridge. Bridge circuit is considered as one of signal conditioning circuit. It is function as a converter that able to convert any impedance variation into voltage variation. The advantage is that we will be able to design an output voltage that varies around zero. This circuit also very sensitive to any changes of impedance. We are going to discuss on DC wheatstone bridge, which is the most common and simplest bridge circuit. And the application of this DC wheatstone bridge is normally as a signal conditioning where it will be used together with a sensor that having changes in resistance, and therefore we need to convert that resistance into voltage. This is the circuit for a DC wheatstone bridge. As we can see here, it is in a diamond shape with 4 resistors. Normally, as for resistor 1 and resistor 2, we use a fixed standard resistor. As for resistor 3, sometimes we use an adjustable resistor. This is to use an adjuster to balance the resistance in the circuit. Lastly, Rx or R4 is actually a sensor that provides resistance change when it measured variable change. For example, like in RTD or thermistor, where it will provide change of resistance when the temperature change. So, for example, we use RTD here. When the temperature change, the resistance will change at the sensor here. Okay, the voltage input, the voltage output is measured here at G, at the middle here. So it is actually a difference between point C and point D here. So normally we write delta V is equal to VC minus VD. The difference between voltage output at C minus voltage output at D. And E here is our power supply. So this wheatstone bridge cannot work without a power supply. Okay. The circuit is very sensitive to any changes or resistance imbalance in the circuit, such that if a very small change in resistance occur at our sensor here in our RTD, for example, this circuit will still able to provide voltage reading, and of course it is very small, normally in millivolt. Therefore, due to the high sensitivity, DC wheatstone bridge is widely used in precision measurement. Now we're going to derive the equation for wheatstone bridge based on this diagram. To start, we write delta V equal to VA minus VB, where delta V is the voltage difference between point A and point B. If we carefully analyze this circuit, we can see there are 2 voltage dividers. This is the first voltage divider, and the second one at this side. So due to that, we'll be able to write VA is R3 divided by R1 plus R3 Vin. And as for VB, it is R4 divided by R2 plus R4 Vin. So from there, delta V is R3 over delta 3 over R1 plus R3 minus R4 divided by R2 plus R4, where we get R3 R2 plus R3 R4 minus R1 R4 minus R3 R4 divided by R1 plus R3 R2 plus R4. Okay, so you can see that we'll be able to cancel this term, so it left us with R3 R2 minus R1 R4 divided by R1 plus R3 R2 plus R4. So this is the full equation for voltage divider. If you notice, I've made a little mistake when I write the full Wheatstone bridge equation on last slide. The correct equation is this one. Can you notice my mistake? I hope so. Alright, so this is the full equation for Wheatstone bridge. Last time my mistake is I write R4 here, not R2. So it's actually R3, R2 minus R1, R4. Okay, so what does null bridge mean? Null bridge. So what is null bridge? So null bridge is when we said that delta V equal to 0. Null bridge happen when delta V equal to 0. So if we put 0 into our equation here, so it will become 0 equal to R3 R2 minus R1 R4. So therefore we will have R3 R2 equal to R1 R4. So this is actually the condition that we need to satisfy if we want to get null bridge. If we want to design the circuit to be null bridge or delta V equal to 0, what normally we did is we assemble the Wheatstone bridge, and then we need to adjust the resistor such that we get delta V equal to 0. So in order to adjust the resistor, we need to satisfy this condition here. The simplest way is to choose R1 equal to R2 equal to R3 equal to R4. Then this condition will be satisfied and we get delta V equal to 0. So why we need to get or to design a null bridge? It is actually because maybe you want to have like at, for example, you have RTD and you say, okay, let's design the circuit such that at 20 degrees Celsius you want to get voltage equal to 0 volt. So by using Wheatstone bridge, we'll be able to achieve this condition. meaning we will be able to design such that the output will become 0 volt when we measure at 20 degrees Celsius. This example is to show how to use the condition in order to design a null wheatstone bridge. So the value of R1, R2 and R3 is given. Therefore, we need to find the value for R4 so that we get null bridge. We already know that the condition to satisfy is R3, R2 equal to R1, R4. So therefore, R4 will be equivalent to R3, R2 divided by R1. So putting the values into the equation, we get multiply by 842 divided by 1000, we get 421 ohm. So in order to get null bridge, we need to choose R4 to be 421 ohm. Okay, example 2.4. Let's solve this example using the equation that we have derived. So the equation is delta V over V equal to R3 R2 minus R1 R4 divided by R3 plus R2 R1 plus R4. So we just need to replace the values of resistance into the resistor here. So R3 is 1, R3 is 120, multiply with 120 minus with 120, but R4 is 121 divided by 120 plus 120, 120 plus 121, multiply with 10. That will give us negative 20.7 millivolt. So the solution is very simple. We just need to replace all the values of the resistors into the equation. Since R3 is given, R2 is given, R1 is given, and also R4 is given. So from there, we'll be able to calculate what is delta V. So this is the value for R3, R2, and R1, 120, and only R4 is 121. So putting the values into the equation and calculate and multiply with a power supply 10 volt, we get the change of value is actually minus 20.7 millivolt. So we can see here only 1 ohm change, and the wheatstone bridge able to give output of minus 20.7 millivolt. You may consider this as to be, first the value is choose to be like this, R1 equal to R2 equal to R3 equal to R4, where all that is 120 ohm. Therefore, we know it will give us null bridge, meaning that at starting point, when all the resistors having same value at 120 ohm, we get delta V equal to 0 volt. But then, the values in R4 is changing from 120 to 121. So, it's increased the resistance by 1 ohm. And due to that changes, 1 ohm changes, the wheatstone bridge able to give reading at minus 20.7 millivolt. This is to show you how sensitive is this wheatstone bridge. Okay, so now we're going to derive a new equation based on a condition where we assume that R1 equal to R2 equal to R3 equal to R4 equal to R. So meaning we said all the values of the resistance is the same. But let's consider R3 is our sensor. 3 is our sensor. So that R3 will have some change of resistance. Meaning, of course, our sensor will change the resistance value. So R3 will always change with some change of resistance, R3. So we're going to derive a new equation based on the overall equation that we have derived before. So, okay, our original equation is like this. R3, R2 minus R1, R4 divide R3 plus R2 multiply R1 plus R4. So this is our original equation. Then we're going to derive a new equation where we consider R1, R2, R3, R4 having same values. Then R3 is our sensor and it will change with some changes of resistance, while the other R1, R2, R4 is constant. Right? So let's put the values in here. So we have delta V per V equal to R3 will change with sum of resistance multiply with R2 minus R1, R4 divide, again R3 has some changes, plus R2, okay, R1 plus R4, alright. And now let's replace all the values here with R. This is R, right? Okay, this is R, this is R, this is R. Okay, all the resistors are R. Only change of resistance that will not change. So this is R. Okay, so we get delta V per V equal to R square plus change of R3 multiplied with R minus R square divide 2R plus change of R3 multiply with 2R. Okay, so then we can cancel this. Okay, so it gives us change of R3 multiply with R divide with 4R square plus 2R change of R3. So let's continue. So we have R change of R3 over 4R square plus 2R change of R3. So we're going to factorize this equation. So we get change of R3 multiply with change of R3 over R. Okay, over R square, sorry, not R cube, R square multiply with 4 plus 2 change of R3 over R. Okay, so this can be cancelled. So we get the final equation is change of R3 over R divided by 4 plus 2 change of R3 over R. Okay, delta V. delta V over V. So this is the final equation considering R1 equal to R2 equal to R3 equal to R4, and only R3 change with some change of resistance R3. So we're going to use this equation whenever the design of the wheatstone bridge is following our assumption, where it said that R1 equal to R2 equal to R3 equal to R4, and R3 is having some changes. Or it can be any resistance actually. It doesn't necessarily be R3. It can be R1, it can be R2, it can be R4. But normally we consider R3 to be our sensor. Now we're going to solve example 2.4 again, but using the equation that we just derived just now. Okay, we have derived this equation. Sorry. Delta V over V equal to change of R over R divided by 4 plus 2 change of R over R. Okay, so from the information given in the equation, in this example 2.4, we do know that R1 equal to R2 equal to R3 equal to 120. And if we consider R4 is our sensor, we may consider that R4 is also 120, but is now changed with sum of resistance R4, 1 ohm. That's why it becoming 121 ohm. Okay, so having this information, we can use the equation that we have derived just now. So meaning we have delta V over 10 equal to 1 over 120 divided by 4 plus 2 multiplied with 1 divided by 120, and it will give us positive 20.7 millivolt. So if you compare with the equation, the overall equation, the full equation that we used before in solving this example, we get negative 20.7 millivolt. But in this equation, when we solve this example using this equation, we get 20.7 millivolt. Can you think why the value is different in terms of positive or negative value here? Okay, that's your task, and I will need you to answer in the WhatsApp group. I will post the question again in the WhatsApp group. As a summary, a wheatstone bridge is a circuit that functions as a converter that able to convert any impedance variation into voltage. So you're able to convert resistance to voltage, or capacitance to voltage, or inductance to voltage. So the arrangement is the same, the equation will be the same, only the difference is the impedance value. Thank you.